Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, so it's a pleasure to have Tom Ristenpart speaking today. Tom is an assistant professor at University of Wisconsin. He's done a lot of great work in cryptography and security, looking at the use of randomness in cryptography, hash functions, format-preserving encryption, and all sorts of things. And in security, a lot of great work in cloud security, in particular looking at vulnerabilities in EC2. And I guess today he'll be talking about cryptographic theory.
Thanks for the introduction. So everyone done reading? Did everyone enjoy the quote? Okay. Whether you agree or disagree is, or if you wrote this quote, that would be awesome, actually. You can step forward at the end of the talk. I'd love to hear who you were and have a discussion. So this talk today will be about cryptography particularly, and kind of this loose kind of viewpoint of what I'm calling practice-driven cryptographic theory. This is joint work with lots of fine people, so I won't read their names, but recognize that they did all the hard work, of course. I'm just taking the credit. So we hear a lot about provable security crypto and doing formal analysis and having lots of rigor. And the usual story we hear surrounding that is that theory we develop, and this educates how we should implement and deploy cryptographic algorithms, or at least that's what you hear in the academic community. But what we know in practice is that we have lots of cryptographic standards, particularly, that have vulnerabilities in them, right? And so there's a bit of a disconnect between in theory, powerful tools we have to avoid vulnerabilities, and the reality that we have a relatively poor track record of completely secure standards. And these aren't just implementation bugs. There are plenty of implementation bugs out there. We haven't solved the problem of getting rid of implementation bugs, but these are problems in the cryptographic designs as well. And there's lots of explanations for this about how standards are developed, and I think most importantly in terms of how it relates to theory, we often find that standards were developed without knowledge of applicable theory that might help, but equally often that these standards were developed before any suitable theory existed. And this, I think, is really a comment addressed to theoreticians who perhaps think theory is all there and ready and happily will help us solve these types of problems. So we definitely have this type of this is my favorite picture from, particularly in light of the Olympics going on right now. We have a lot of pressure on our athletes to not repeat this. And we might think that in the crypto and community, we also have a little bit of a baton dropping situation, that you have theorists on the right trying to hand off some information or knowledge about how to design crypto to practitioners on the left, and something gets dropped. What's that?
He's got a baton.
He's got a baton?
No.
No baton? No baton? No baton. Uh-oh, baton.
Well, what about the green baton?
That's the bottom guy.
Oh. So this guy doesn't have, let's see, this is, sorry, it's a bad resolution picture. I think NBC or the Olympic Commission copyrights all the high-res pictures of this or something. So the only ones I can steal for free from online, which I shouldn't say that when being recorded. Yeah, this is, I think this is the guy who won the race, actually. So maybe that's like the static analysis community or something doing better than cryptographers. Anyway, so there's a baton being dropped. So today I'm going to basically talk about kind of trying to change the viewpoint a little bit. Instead of thinking about theory educating standards, let's look at it completely opposite and think about how we might derive new theory surrounding, in particular, cryptographic standards, right? And so we'll take standards as ground truth and try to understand, use theory to understand better what they're giving us or what they're not giving us. So in particular, this will, give a, I'll basically apply this very high-level approach to a bunch of different projects, and we'll talk about each project in turn. But the idea is that we're going to, first start by looking at standards, right, and understand, try to understand from them what are the often implicit security goals, and then match them to, existing formal definitions from cryptographic theory, or provide new definitions, which we'll often see that we don't have appropriate formal definitions of security. for these types of tasks. And then use our theory now as a post facto tool to analyze the schemes in these standards, the cryptographic schemes. And this will help us clarify the security posture of these systems, either by helping us suss out vulnerabilities that were previously not known, or provide proofs that can help us improve confidence in the cryptographic schemes. Okay, so with that viewpoint, I'm going to talk through a few different recent works that all follow this this regime. One is a bit older. I talked about this last year a bit, the TLS 1.2 record protocol. I'm going to talk about it again for those of you guys who haven't seen it. And then I'll talk about newer work that will be appearing soon on password-based cryptography and the HMAC construction. Okay, so let's just get right into it with TLS and kind of skip over some of the basics. TLS is used everywhere to protect web communications. And it consists of two main cryptographic portions. One is the secret key exchange protocol to derive a shared secret key. And then that shared secret is used to send data via the TLS record protocol, which is aimed at providing confidentiality and authenticity for communications. So we'll be focusing on just the record protocol portion of this and not concerning ourselves further with the key exchange. So inside the record protocol is a particular cryptographic encryption scheme that we call the MAC encode encrypt. This is also sometimes called MAC then encrypt algorithm. And the idea is that we're going to provide an all-in-one solution via two parts. Right? First, we're going to take our payload data and authenticate it with a message authentication code. And then we're going to encrypt the result of concatenating the payload with the tag and some padding, if needed, with an encryption mechanism. And then send the result along the public channel. Okay, so there's lots of different algorithm cipher suites that are used inside TLS. We're just going to look particularly at the CBC algorithms for underlying this MAC encode encrypt. Okay. So what happens there? Well, CBC mode within TLS works as follows. We take the payload, the MAC tag that we computed already, and then we have to pad out the resulting string in order to get a bit string that's a multiple of the block size underneath that's used inside CBC mode. So if we're using AS, this is 128 bits. And so we need to have a multiple of 128 bits. And then we use CBC mode, standard CBC mode, on the result as so. So the most recent versions of the standard, they use explicit initialization vectors. So this is where you choose C0 randomly each time you encrypt a new message and send it across. This is not what they did in prior versions of the standard and before they used like the last ciphertext block of the previous encryption. Okay, and then of relevance to our results, particularly are going to be the padding choices that can be used in TLS. And basically, it's this regime where you pad out with bytes, and the byte value that you use is indicative of how many bytes of padding -1 that you have, right? So if you have to pad out by 1 byte, you use 0, 0. If you pad out by 2 bytes, you use 0, 1, 0, 1. 3 bytes, 0, 2, 0, 2, 0, 2. The idea being, of course, from a practical perspective, is very nice, right? Because you just read the first byte. That tells you how many more bytes you have to remove when you're decrypting. And moreover, CBC mode or TLS allows extra padding, right? So you don't have to do just minimal length padding. So to get out to the next boundary, n-bit boundary, or the block length boundary, but you can also pad out further, okay? And the reason they do that, as indicated in the standard, is that this is a countermeasure thought to help prevent traffic analysis attacks, basically that analyze the lengths of particular messages, right? So by padding out extra amounts, you can hide how long the message was, or at least that's the idea. Okay, so to summarize on the padding choices, there's two that the standard supports. One is minimal length padding. You just fill up enough to get to the next block boundary. Or you can have extra padding. And so you'd have extra blocks of padding beyond what would be minimally needed. Okay, and most implementations use minimal length padding, but some do use extra padding, like new TLS by default they choose a random amount of extra padding each message to, again, try to frustrate traffic analysis attacks. Okay, so the first thing we noticed when we sat down to look at TLS was that this length hiding goal that is explicit inside the TLS specification isn't well addressed by existing definitions, so we rectified that. And this was technically straightforward, right? We took existing definitions and extended it to a length hiding setting that also seeks to hide not just the content of messages from adversaries, but also the lengths. And then given that tool, we wanted to do analysis of the TLS record layer. And in this first work, which is the older stuff, which I've already talked about, which I'll explain again, we point out that actually there exists an attack in the case that you use truncated MACs with TLS, MAC encode encrypt, and this variable length padding. And then we show that if you don't meet the preconditions of this attack, that you have basically at least one short message and a short tag and variable length padding, then everywhere else we get positive results about security. And so I'll mostly talk about the attack because it's cute and simple. And then more recently, this somewhat prompted us to try to understand the benefits of this type of padding-based approach. And we recently had a paper discussing traffic analysis attacks against these types of countermeasures. And I'll just briefly mention the results about that and point to maybe pique your curiosity to go look at the more extensive results in the paper. So the very short takeaway is that the tag size matters in using MAC encode encrypt, not just here in TLS, but if you use it elsewhere. And if you have a setting like this where the tag is short, you have a message that's short, and some of the padding ends up in the first block, then there can be distinguishing attacks. And otherwise, you are OK. There's a pretty thin line between security and security. OK, so just to give the attack setting a little bit more concretely. So we have an attacker who's a man in the middle, and we have a client on the left and a server on the right. And the client's going to encrypt some message X. Let's say it's either yes or no, just for concreteness. Note that these are two different length messages, right? If you assume that they're encoded as a byte per letter. And the goal of the attacker now is to determine which of the two messages was encrypted, right? And so he gets this ciphertext. And what he's going to do is now maul the ciphertext. So he's going to modify it and then forward on the result of mauling it to the server. And then look at how the server responds to see whether it was yes or no. OK? This is a classic active man-in-the-middle attack. OK, so let's set some numbers. So we have a tag length of t equals 80. This is a classic choice for truncated tags. A blanc length of 128, which corresponds to AES. And now I'll just draw out the two cases we have for C based on whether it's yes or no being encrypted. In particular, and we'll have one extra block of padding, which is I assume we're trying to hide lengths beyond the first n bits. So if no is encrypted, then we end up with encryption and padding that looks like this. So we have the 2-byte no, the 80-bit tag, and then we have 4 bytes of padding filling out that block, and 16 bytes of padding in the following block. So that's in hex, I guess. So yeah.
Could you remember what do you mean by hiding the tag, the length? You're hiding just one block.
Well, so if you extend out to another n bits, in theory, if it's a secure scheme, the adversary shouldn't be able to tell whether you have encrypted message that's of any length between like 1 byte all the way up to 2n minus 1 bytes, right? So all of those should look the same to the adversary because he'll just see 3 random-looking blocks of ciphertext. Okay. So if you choose to do this, then you end up, one of those messages you end up encrypting is just 2 bytes, then this is the result you would have. Okay? Does that answer your question?
I think I'm just looking for a simpler answer.
Oh.
Are you just trying to hide how many bytes in the last block are message and not message?
Right, yeah. So the adversary shouldn't be able to tell whether there's 20 bytes of padding or 1 byte of padding, right? That's, yeah, because it's all encrypted by CBC mode. Yeah. OK, so then the other setting is if we have a yes message being encrypted, right? And that means we have 1 less block of padding, byte of padding, excuse me. And so you subtract 1 from 13, you get 12, and makes the slide generation easy. OK, so we have these two situations. It could have been one of these two situations. The adversary wants to figure out which, right? And so now the attacker he gets C0, C1, C2, and he's going to apply the same mauling procedure, or he's going to apply a mauling procedure to it, and it'll do 2 different things based on which of the 2 messages was actually encrypted. So here's what the attacker does. He takes the first block that he gets, C0, and he XORs into it 1, 0, the byte 1, 0 to the 4th. Okay, so that means 4 bytes with the 5th bit set to 1, right? And the rest all zeros, okay? And we'll see what that does in a second. And then he basically deletes the last block, doesn't care about it, and forms a new ciphertext that's C0 prime C1 and sends that on, okay? So in the first case, we've thrown away the last block. We've flipped 4 bits in C0, and that ends up flipping 4 bits of padding when the recipient does decryption. And so in fact, this will decrypt just fine on the receiver's end. Okay, the MAC will check out, the padding is correct, and the server will be happy with it and continue on with its communications. Now in the case that the message was yes, so what happens? We've thrown away C2, we've flipped 4 bits here. That changes the padding to be the correct values here, okay? But we've also flipped 1 bit of the tag. And the security properties of our tag the tag is a deterministic function, so it's not going to verify, and the server will reject this decryption as invalid. Okay, and in particular, what the TLS spec says, then the connection will get torn down, and so the attacker will see whether it was no or yes. Okay, so this attack works particularly because you can use the IV to flip bits in that padding, but that only works if you have padding that is inside the first block of CBC encryption. And so fortunately, with the cipher suites that are chosen in TLS, that doesn't exist because the MACs are always larger than 1 block in length. If you use truncated MACs, which is a common thing to use in specs as indicated like an RFC 6066 for TLS, then the attack could apply. Fortunately, we looked around quite a bit to make sure nothing was actually vulnerable in practice right now, and it looks like that's the case for the moment, so no one's using this particular combination that's vulnerable. And of course, that leaves the question of what happens with all these other cases. I won't go into the details, but we analyzed the security, and we showed that, OK, if you avoid this one corner case, you basically can show security. OK, so as I said before, this prompted us to try to understand what, we were kind of curious how far this length hiding security actually takes you in practice. And in particular, there's been this long line of work on a particular traffic analysis setting that TLS, in theory, should be able to help protect against. And the idea is you have an attacker who's, again, a man in the middle, but this time passive. And it's going to be viewing ciphertext being sent back and forth between some user and an HTTPS proxy. That means you're going to funnel your website requests over a TLS tunnel so that the IP address and everything is about the destination website is hidden, and the proxy is going to forward on your request to some server. And the idea is that attacker shouldn't be able to figure out what website you're visiting. Okay, because if you're using Tor or any of these privacy enhancing, any of these privacy enhancing technologies, this is an attack setting of interest. And so this is called website fingerprinting because you're trying to, the attacker, say gets he wants to fingerprint what the destination website looks like in terms of ciphertext flowing back and forth, and then later figure out if this is the same website that you're visiting. And so the usual thing in the academic literature is to look at a so-called closed world setting, so the attacker knows like the set of possible websites that you're going to visit. And the state of the art is to use these types of supervised machine learning algorithms to try to train on labeled data. So you set up your own system to visit websites, train a machine learning algorithm to classify whether it's website 1 or 2 or 3, and then you take that machinery in theory, you can go and apply this to an active attack setting. So there's been a lot of work on this, as I said, and we couldn't really figure out what the conclusions of this work were, because particularly most of the works had been in a setting where there was no countermeasures like length hiding, authenticating encryption, and being used like in new TLS. And so we wanted to understand how much these countermeasures like the LHE countermeasure in TLS can help. And so we had a poor student go and implement all sorts of different attacks from the literature, including some new ones, simulate a variety of these countermeasures, including things like the TLS countermeasure, and gather some data sets that had been used in literature previously. And then for all these variables, run extensive tests to see how good this attack can actually work, how well this attack can actually work. And so the results are what we thought were pretty pessimistic. So this chart shows the average accuracy, taken over a bunch of runs, of figuring out which of K websites a particular user visited when using a variety of countermeasures. So none is just like raw encryption without any length hiding or padding mechanisms. And then there's a bunch of other ones like pad to MTU, session random 255, packet random, this corresponds to TLS, what you can do in TLS, like what new TLS does. And then a bunch of other ones, including more advanced things that I want to explain, like traffic morphing. And what we found is that you basically can set up a very simple machine learning algorithm. Yes?
Why is the exponential countermeasure worse than no countermeasure at all? Isn't that what it's saying?
Where is this?
So the exponential thing.
Yeah, I mean, so the it's not clear that it's like a linear thing, right? Like having countermeasure, the countermeasure might actually increase the. Let me explain what the classifier is, then I'll get right back to your question. So what we show is a simple naive Bayes classifier that really just took a few features from this traffic, right? So instead of looking at individual ciphertext lengths, what it did is look at much coarser information, like the total bandwidth used in either direction by the connection, the size of bursts and the number of them, and like the total time for the connection, which is a bit of a difference from what the prior works have been doing. They've really been focusing on individual ciphertext lengths as the important feature. And so this is what this VNG++ classifier did. And so to get back, before I give you just the closing thing here, the punchline is that these countermeasures like pad to MTU, no, which one were you looking at? Exponential can actually exaggerate some of these features for us, right? Because you're padding, so it might separate better the total bandwidth used by one website compared to another website, as compared to using no countermeasure at all. And that's a rare case. Generally speaking, the countermeasures do a bit better than no countermeasure, but it's not necessarily always the case. Does that answer your question? Yeah.
I thought it was the other way around. Isn't higher better in this graph?
For the attacker, yeah.
Yeah.
Yeah. So the attacker's doing better against exponential over here than none. Yeah. Yeah. So it's a great question, and the answer is that just for these features, it turned out that that actually exacerbates the phenomenon. Okay, so the point being that length hiding can be helpful in settings where you're really worried about these fine-grained lengths being revelatory, like yes versus no, but seem to be less helpful, maybe not helpful at all in settings such as website fingerprinting. Okay, and this is just like we did a lot more analysis in the paper. It was a survey paper looking at all these things and doing new analysis of all these various algorithms. Okay, so that was looking at TLS 1.2, showed we gave new definitions that I didn't talk about, but they're in the paper. New attack that wasn't known before, and Also looked at, I guess, this traffic analysis stuff, which I didn't explain in too much detail, but you can go check out the paper. So now I'll move on to password-based cryptography, unless there's any further questions about TLS. OK, so PKCS number 5 is basically the standard that helps us answer the following question. We have an encryption mechanism like CBC mode, right? It expects a encryption key that's uniformly selected at random from some space of bit strings. So if you're using AES, you expect a random 128-bit key. But in practice, of course, we'd often like to encrypt our data with a human memorizable password, right? So mine's like 1, 2, 3, 4, 5. Clearly not a uniformly selected bit string. It's 128 bits. So how do we do it? And PKCS number 5 is a standard that was developed or published in 96 or something, 1996. And it's been around for a long time that speaks to how to deal with this. And the solution is very natural. It's to use what's called a password-based key derivation function, or PBKDF. So the idea is we'll take our password, 1, 2, 3, 4, 5. We will choose a random salt, okay, which is just a uniform but public bit string of some length, say 64 bits or 128 bits. We'll concatenate those together, and then we'll hash that result with a cryptographic hash function like SHA-1 or SHA-256 nowadays. Then we'll take that output and we'll hash it again. We'll hash again and again and again. We'll do that C times to get a bit string, and then we're going to use this as our key for CBC mode. Of course, if it's a little bit longer, so we can truncate K if we need to. OK, so the algorithm in pseudocode is as such, right? You get a password, you get a message, you choose a salt, you hash it C times, the password concatenated the salt, and you encrypt it with whatever your underlying encryption mechanism is. And you output both the salt and the ciphertext now as the resulting ciphertext. OK, so this is used really widely, or variants of it are used very widely in tools like WinZip and OpenOffice, even Wi-Fi, WPA to do derivation of session keys uses one of the PBKDF functions in PKCS number 5. And despite that, there hasn't been much analysis of this standard. There was one paper a few years ago which did a little bit of work, but wasn't very satisfying. And otherwise, there hasn't been much to say. And so we wanted to understand there's some, get a better understanding of it. So the first thing we realized is that, and I'll explain this more, is that, again, here we have no theoretical notions that really were satisfying in terms of measuring the efficacy of the measures, the mechanisms underlying PBKDFs. In particular, we needed a new framework for defining what we're calling multi-instance security notions that measure kind of the hardness of breaking many instances of cryptographic objects in parallel. And then we analyzed PKCS number 5 using this new framework, give some proofs of security amplification for them. So we basically prove what you would expect to be able to prove about them. But nevertheless, we're the first to offer such proofs. And we have some, what I think are nice simulation-based techniques that we think will be applicable to places beyond just like password-based encryption, but elsewhere as well. OK, so the question, the first question is really, why do we need new theory? It seems like this is a pretty straightforward thing to analyze. It's encryption. We have lots of encryption definitions. So why can't we just use one of them? Well, let's see. I'll give you a kind of the most obvious approach to defining security for a password-based encryption scheme. And this is basically using the classic indistinguishability under chosen plaintext attack notion. So let's fix set D. That's the set of possible passwords. Okay, it's not all 128-bit strings anymore, but it could be some set of possible passwords that people choose. And we're going to define security this way. So we have an attacker that's going to play a game with a challenger, which is the gray box on the right. And the attacker queries 2 messages, M0, M1, okay, of his choice. And what the challenger does is it picks a password. Well, for simplicity in this talk, just assume it's uniformly chosen from this set. He also picks a random bit B. And then he encrypts using our PB, like our password-based encryption mechanism, one of the 2 messages based on bit B under the password, and then returns the result. Okay, and the adversary wants to figure out which of the two messages it is. Okay, so he guesses a bit B prime and wins if he got it right. Okay, so this is nothing exciting, right? This is the if you're a cryptographer, maybe it's like super exciting if you're not. This is the classic IND-CPA definition, just with passwords as opposed to keys, and of course just the single query version for simplicity, but it's easy to extend to multiple tries by the adversary. Okay, so under this notion, you can prove. Well, this is a corollary of our later results, but you can prove the security of PB encrypt using this hash-based construction. And in particular, get a statement that works in the random oracle model, so assuming H is ideal, that says basically that the advantage of any attacker in this game is bounded by Q over C times N, okay, where N is the size of this dictionary of passwords. C is, again, this iteration count of the hashes, and Q is the number of hashes, hash computations, hash queries that the attacker can make. Okay, and this is what we would expect, right? Because this matches a very brute force attack that works in time close to CN, right? What do? You just try all of the passwords. So you hash C times each of the passwords, and you try decrypting the ciphertext to see which of the two messages it was. So that's good. So it's tight with a known attack, and so this seems to be the best we can do. So there's two issues that remain. One is the kind of obvious thing that everyone knows about passwords, which is that passwords suck and N is small, right? And so it's fundamental in this setting. But even if we have N approximately pretty big, like 2 to 31, we can set C pretty large. Like a common choice is 10,000. We can't set it too large because it might slow down functionality. So like something like 10,000 is what's used in WPA, I think, for example. But still, this means that you only need, and our proof works, showing that you need only, that the best attack you can do is the brute force attack, right, which requires about time 2 to the 44, which by today's standards is getting pretty narrow. Okay, this is like a fundamental limitation of passwords, okay, and we're not going to hope to do better than that. But there is something else that's kind of suspicious about this whole analysis, which is that we never said anything about salts in the whole analysis. And so remember a slide ago, I said that there's a salt being chosen and randomly. It's S bits, but you notice nothing here about S, nothing about salts arises in the theorem statement. So from the point of view of IND-CPA security, salting doesn't matter, which stands in stark contrast to the fact that we all well know that salting matters really a lot in practice. And so let me explain why. Okay. And the reason is that salting helps quite a bit in what in a so there's two reasons salting works is very important. I'll talk about one of them. One is that pre-computation attacks become harder, right? If you don't know the salt a priori, there's an issue. We're giving the salt to the adversary right away, so he gets it right away. So we'll talk about the other issue, which is that salting helps in this what we're calling multi-instance attack setting. So now let's think about a new attack model in which the attacker gets access to basically M different challenges. So say he's getting C1 through CM, which are ciphertexts of independent messages, M1 to MM, encrypted under independent passwords chosen from the set D. Okay? And his job is to recover the messages. Okay, so what do we know? Well, we know the best known attacks are such. So with salts, we get that the best known attack takes time approximately MCN, right? Because you have to brute force, or the attack brute forces all M passwords, and each M of the passwords takes CN time. Without salts, there's a faster attack, right? Which takes time just C times N plus M times N, right? Because you can use like rainbow tables to compute for each possible password. Let's see, wait, for each possible, for each possible thing, you compute the hash. You can use some time-space trade-offs if you want. But anyway, the point is that you lose the multiplicative by M factor in the attack. Okay, so we saw that, this is the best known attacks. We'd like to prove again that we get what we expect, which is that breaking M encryptions requires MCN time. But now to prove something, we need to have a definition of security. I just showed you that IND-CPA actually doesn't speak to this notion of security at all, so we need a new one. Yeah?
You need breaking M encryption mean? Does that mean break one of them or all of them?
It means breaking all of them.
All
yeah.
of them. Okay.
Yeah. So breaking one of them would be like the traditional like single instance security setting, what we're calling a single instance security setting, right? So IND CPA. But here we're really saying you need to break all of them. And this is one benefit of salting, that is, as you try, it gives you a second line of defense, so to speak, right? That even if you can brute force one password, you may not be able to brute force a million passwords. And we'd like to be able to show formally that is actually enjoyed, okay? Okay, so we need new definitions. So I'm going to walk you through defining not multi-instance security, but just two instance security, because it fits on the slide nicely with having two challenge boxes as opposed to many, many. And so the first attempt that we had at capturing this role of salting and forcing this MCN multiplicative factor improvement in security is to use what's called the multi-user setting, which is from Bellare et al. And the idea is now we have two boxes, right, with two different passwords, okay? And the attacker can query both of them with messages. And he gets back from either one the same left or right message encrypted under that particular password. And his goal is to guess what the bit was, okay? So this is defining indistinguishability when you have access to multiple different instances of the cryptographic primitive. So this doesn't work for us, okay? Because actually the best attack, again, here works in just CN times as opposed to 2 CN time, right? Because as soon as you brute force one of the passwords, you learn the bit that was used for both boxes, okay? So that doesn't help us. So the next natural thing is that, okay, we need independence completely between these games so that they're totally separate. And so what we do is have an independent challenge bit as well as independent passwords for both boxes, okay? And so the attacker, again, gets to interact with both these boxes. Now this becomes what I guess people in the amplification literature would call like a direct product game. So you have two independent copies of the game that the adversary gets to interact with. And so the question now is, how do we gauge success? There's two challenge bits. The most obvious one, which could be fine, is that the adversary tries to guess both of the bits. Okay, so this is like an AND measure. He has to win against by guessing both, and we can subtract off the trivial probability of winning, which is a quarter here. Right? There's two random bits, so the trivial probability of winning is a quarter. We find this not particularly convenient to work with. I mean, mathematically it's a fine definition, but it's not convenient to work with. For example, it doesn't really capture breaking both instances. The advantage measure doesn't really capture breaking both instances, because as soon as you break one, you can just guess the other bit, and you get constant advantage, like 1/4, where we would expect that to be 0, because you haven't really beat both instances. You just guessed against one of them. So we can solve that by changing the advantage measure a little bit to make it more convenient to work with, which is to use an XOR. Okay, and this has, this basically gets rid of this weirdness about having constant advantage, even though we've only broken one of the instances, and so that goes to 0. Okay, and this is basically our suggestion that we think this is the kind of the nice one to work with. It's called the XOR measure, and you can of course extend this to multiple instances. And actually, this is just for encryption, but you can do it for lots of other settings. And in the paper, we talk. Yeah, there's a question?
Yeah.
Or is it a stretch?
No, question. So doesn't the Bellare paper discuss why they chose the same bit?
Yeah,
I think it was about having one message be a function of the other.
Right. So so I should have said that this was not a suggestion for our problem. This is just something that seemed like it could be useful in our setting. And so the multi-user setting was suggested for a different reason, which was to look at how to do efficiency improvements for like public key encryption schemes. And you're absolutely right. There's something about whether you have a bit that's joint across the games or independent, which dictates something about what you're learning from each of the individual encryptions. So if there's a joint bit, that means the information that you're learning potentially from the boxes is correlated across the boxes. And if there's independent bits, it's like independent information that you're learning from two different challenges. So to measure the hardness of this type of multi-instance attack where you really have to break M things, you need to have the independence. Otherwise, there's nothing to do. right? For the m+1th, or the next instance. If you already know what the message was, there's nothing left to do. So you don't have to break the password, right? It's a great question. Yeah.
Yeah, they were looking at breaking any single one.
Right. Right.
You're looking at.
Right. And don't get another point of clarification, which is a great opportunity to bring this up. We're not saying that just breaking one instance is okay, right? Obviously, that's a bad thing too. What we're trying to get at too is why salting helps us also get this other measure. So ideally we would of course like to have that breaking any single instance is very hard, but in passwords that's not the case, right? So we'd like to have the second setting where at least you can't break many instances.
There's a bug in your slide.
Oh, I disagree. I don't know. Is there actually?
It's almost out.
Oh.
It's up
This
in your
guy?
description now. Yeah. It's okay. It's gone. Oh.
Not quite. I think I saw that thing floating earlier. I thought I was just freaking out, but someone put something in my coffee this morning. Okay. Measure, XOR measure, right. Lots more in the paper. I mean, so this is a very general thing, right? You can define multi-instance security for many places, and games like this have, like XOR lemma type results have come up, are very related, but not the same as what we're targeting. So anyway, there's like a lot to explore in this setting, and I won't talk about that much more. And the thing that's interesting and maybe not surprising, people work in like amplification settings, is that things get technically very challenging from a formal like proof setting here. So for example, things that were surprising to us is that a very classic technique of hybrid argument, which is very easy to use in the single instance setting, becomes very messy in the multi-instance setting. And so if that was meaningful to you, you can ask me about after the talk what more about that. Okay, so back to the practically relevant thing, which is how to apply this to PKCS 5. Well, we go on to give a indifferentiability style notion, which I won't talk about, that helps us with some of the proofs. And we're able to show that indeed we get the type of phenomenon in this multi-instance setting that we expect. So we've gone from this Q over Cn to this Q over MCN, which matches the attack that we know works, right, in MCN time when you have salts that are sufficiently long. Okay, so as long as your salts provide independence between all the points, then between all the instances, then the attacker really does need to brute force all M passwords. Okay, so yeah, any questions? Yeah.
At all getting rid of the random oracle assumption, or is it inherent in this?
Yeah, so it's a great question. It's hard to say it's inherent, but it would require a huge. I mean, so basically, all this setting is in a place where you basically can think of n here as just making this a flat set. So this is like 2 to the min entropy of the passwords, right? But passwords here have low min entropy, so we're talking something very small, which means that you can't use LHL or any of the standard model techniques we know. They just won't work, and provably won't work, at least for existing kind of known universal hashing constructions. So that doesn't work. The other thing, we don't know how to prove like the times C amplification if you go into the standard model, right? We can show, and it's not trivial because you have all these chains of potential, like you kind of think that you have M different chains of random oracle queries that he needs to fill out, and you need to show they don't collide and overlap and do weird stuff. We definitely wouldn't be able to show anything about that in the standard model. And yeah, likewise, I think the M factor is also something that would be hard. So it's a great question. I mean, basically, I think at this point, for low entropy inputs, when you're trying to do things like extraction, we have no idea how to do anything in the standard model. Ugo's had some very nice work on this, kind of pushing the boundary on this direction, but I don't think it yet says much about this. But maybe he'll have more to say about it soon. And in certain, in practice, this is matching what we expect the hash functions are giving us. So, any other questions? Okay. So, yeah.
Did you look at related passwords? Is there any difference?
So yeah, it's glossed over here. In terms of related passwords, I mean, we don't say much about this set n, so you can imagine this So actually, this is a simplification. In the paper we look at, we don't even actually fix any particular distribution over the passwords. They could be totally related. And what we show via this PBKDF indifferentiability style thing is that you basically extract all the entropy from the password space. So if there's, so you wouldn't get a nice closed form analysis here, but you show that all the, even if you have related passwords, you get all of the security. So if you have one guy has a password that's like 1, 2, 3, 4, 5, the next guy has 1, 2, 3, 4, 5, 6, and that 6 was chosen uniformly from 0 to 10, then we get, whatever entropy the first thing gave, which is 0 plus, the 1 over 10. Yeah, anyway, so the point is, yes. The answer is yes. Yeah, and it's kind of one of the benefits of doing this simulation style approach, which it helps with these types of things, yeah. Yeah?
Are there two versions of the PBKDF function?
Mm-hmm.
And so does this result apply to both, or one, or?
I'll mention passing in the next, no, maybe I won't actually. So the other one uses HMAC, and I'm going to talk about HMAC next. And the result works if HMAC is a random oracle, which we'll talk about next. Fantastic segue, thank you very much. So okay, let's talk about HMAC. So just to set the stage, HMAC, for those of you who don't know, is a keyed hash function. And it was designed originally to help with problems with length extension attacks in the setting of secret key cryptography. So it was designed with the idea that K is going to be a secret key, like uniformly chosen, and M is some message that you're trying to authenticate. It's used widely as a message authentication code in TLS, PKCS, SSH, IPSec, pretty much anywhere you look. And there's been quite a few analyses of its security in this uniform secret key setting from the provable security side of view. Of course, there's also all sorts of like cryptanalytic work analyzing it as well. Okay, so a little bit closer look at it. Most often in papers, including some of mine, I kind of stop at this view of HMAC, but for the purposes of this work, it's helpful to get a little bit deeper. In particular, HMAC is has structure to it. It's not just a hash function. So use the hash function twice. And what it does is it takes this key K, does something I'll mention in a sec, transforms it a little bit, and then XORs it with IPAD, which is a constant bit string, and then concatenates the message, hashes that, takes the modified K, XORs it with a different constant value, and then concatenates that to the result of this, and then hashes the final thing, and that is the output of HMAC. Okay? Okay, so I glossed over some details, which is consistent with most of the academic literature on this. And in particular, the actual pseudocode for HMAC is this, right? So what you first do is you check to see if the length of your key is greater than d bits. D is a parameter of the underlying hash function. So if the hash function is like Merkle-Damgard, this is the block size of your underlying hash function. So with SHA-256, it's, oh boy, I just talked myself in the corner there. 256 bits, 512 bits? Someone who actually knows something, please. 64 bytes. Now I have to multiply it by 8. Anyway, let's forget about it. It's D, okay? And then, good. So K, and if it's longer than this D bits, you first hash it with the hash function, okay? And this gives you this K prime. Otherwise, we'll just set K prime to K. And then what do? We then make sure that we then pad out K prime to get D bits, okay? And we do it with zeros, okay? And then that's K double prime, as I showed up there. And so then we XOR it with IPAD, which is D bits, up here to get this H, and then down here, OPAD, which is also D bits, 2 different D bit strings. Okay, hopefully that's consistent with people who've actually looked at HMAC's view. Okay, good. Okay, so, and this is really nice. HMAC is a great, kind of Swiss Army knife. It's got 2 inputs, right? They both can be arbitrary lengths. And so both arbitrary length keys and arbitrary length messages. And this is great because it makes it very useful in a broad variety of settings. So, and indeed, it's become used in so many, many different settings. So for example, the PBKDF question, right? There's a password-based key derivation function based on PMAC where now we use the password as the key for HMAC, which is, again, the arbitrary length is nice, passwords are arbitrary length. And we use as the input the salt. There's some other information too, but just think of it as a salt. And then we hash it once, and then hash it again using the password each time for the key of HMAC. This is actually a simplification of PBKDF number 2. There's some other stuff going on, but this is basic structure. OK, and of course, this is not a uniform secret key anymore, which is important. So these other analyses don't apply. Excuse me. There's been lots of other suggestions, at least in other places, for using HMAC in other ways that are kind of outside this traditionally envisioned use. So Ugo's been suggesting this very nice construction HKDF for doing kind of general purpose key extraction, where he uses the key input for HMAC as a public salt value. TLS 1.2 actually already does things somewhat like HKDF. It uses HMAC as an extraction mechanism, not like HKDF, but for the same type of purpose as what HKDF would solve. And in there, K is, again, a non-uniform secret like a password, PKCS number 5. And then I've used HMAC in some other places as well, where K is a non-uniform secret. So the question that came up was, OK, we have analyses when K is a uniform secret. What's going on when we don't have a uniform secret? And we'd like to understand if these other applications are good. So applying our approach, the first thing, we actually have a notion of security that we thought was good for this. It's called indifferentiability from random oracle. And this is offered by Maurer et al. And this basically says that HMAC, altogether acts like a random function on 2 inputs, right? So if you change the key or you change the message, you get a totally different independent-looking output. That's the very, very high level. OK, so then we did some analysis of HMAC to try to show that it was indifferentiable from a random oracle. And what this popped out was that there's some issues. One is that there's, I say weak keys, but we really should call them weak key pairs in HMAC. And this it relates to something that I've been calling the second indifferentiability paradox, which my co-authors hate that name, but I think it's really cute. So you can decide for yourself. And I'll explain that too. And then we recover some positive results in the cases that HMAC avoids these weak key pairs. OK, so let's see. Running low on time. Let me just say briefly, so why do we want to do indifferentiability from random oracle? Well, I said before that we had proven that HMAC is when it's used inside PBKDF2 is good, and that's true if we model HMAC as a random oracle, so a function that outputs random things. Indifferentiability formalizes this notion of being indifferentiable from a random, formalizes this notion of behaving like a random oracle, and would in particular allow us to show that this theorem works when you take into account the structure of underlying HMAC, this 2-hash construction plus the key massaging. OK, so let me skip some of the high-level discussion of that, and let's give a little bit of history, because there's some confusion about the indifferentiability of HMAC, both by myself and others. So in particular, in the first paper that suggested indifferentiability as an analysis tool for hash functions, they analyzed a construction that they called HMAC, which is not HMAC. And I've yelled at Yevgeniy about this, and he just yells back at me, so we have a nice time. Anyway, it's not HMAC, it's standardized, so it didn't apply. But I mean, people, I read that and I was like, oh, yeah, it looks like it's fine. And it actually looks like the techniques they used for that proof should work for real HMAC too. So it seems like everything should be good. And so there's been lots of works, myself included, assuming that HMAC is a random oracle. Krofcheck, suggested that the CDMP05 proof extends to HMAC, but didn't get into details, and certainly it does look like it should. So we were curious to figure out if this was actually the case and go do the due diligence on figuring it out. And this is where we came across these weak key pairs. OK, so if we go back to our description of HMAC, which is not what people in those prior works really thought of HMAC as, but it is really HMAC, we can see actually that there's immediately a troubling issue with the way key handling is done. And I hear laughter in the back. So I've highlighted the troubling issue, which is that if you have keys of different lengths, this is an ambiguous encoding, right? And so in particular, this gives rise to what we call colliding keys in HMAC. So this is any two keys K1, K2 such that they're not equal, but HMAC of K1 on a message is equal to HMAC of K2 on the same message. So an example of a colliding key pair is just a key K1, and then you add a 0 to it, and you get a key K2. And you can verify for yourself that HMAC is going to treat those two keys as the same value, or the output will be the same. And this is clearly not what you would expect if you thought HMAC was going to give you random looking outputs for any different K1M, K2M. And so, of course, and this does indeed give a very trivial indifferentiability distinguisher. I guess if you had settings in which you had related keys that looked like these types of relationships, then you'd have a relay key attack against HMAC. So it's not that great. But definitely you avoid this problem. And I'll talk more about the practical implications of this in a couple slides. You can ask questions. The sky is not falling yet, but this is very interesting. So the colliding keys don't exist if you use fixed length keys, okay? Assuming H is collision resistant, I suppose. So these are keys of different lengths, so it doesn't work. But even when you do that, which remember this is like the original design goal was for like uniform keys of a particular length. Even if you do this, then there's another slight issue that arises in the way that the differentiation between this internal application of H and the external application of H gives. And in particular, we get what we call ambiguous key pairs. And this is any keys K1, K2, such that after you process with this pre-processing to get K1 double prime and K2 double prime, you have the equivalence that K1 double prime plus IPAD is equal to K2 double prime plus OPAD. I'd probably never mention this. Hopefully everyone picked up. This is XOR in reality. Okay. Okay, so what does this mean? This means that there's not strict domain separation between like the internal application of H and the external application of H. And so examples of ambiguous key pairs are obviously like any K1 such that you define a K2 that's equal to K1 plus IPAD plus OPAD, right? And this particular works when K1 and K2 is equal to D, or you can also do it when size of K1 and size of K2 is equal to D minus 1. And I don't think you can do it when it's equal to D minus 2 because that's the first bit that's different between IPAD and OPAD. And there's other, other settings too, but kind of narrow corner case in terms of the key space of HMAC. And so, right, no domain separation. It's not clear. This doesn't give rise to trivial kind of issues like the colliding key pairs do, but does cause problems for proving indifferentiability of HMAC. And in particular, one can, we gave a lower bound on the indifferentiability of HMAC. And so it's a bit technical, and I haven't even told you what indifferentiability is technically, but the point is we basically show, the implication is the most important thing, that the lower bound rules out having proofs, indifferentiability-based proofs that give good concrete security bounds. I can offline tell you more about the details underlying the technical issue. Instead, I'll talk about my favorite term, which is this second iterate paradox, which has the same similar structural issues as what happens from ambiguous key pairs in HMAC, but for a simpler construction. And this is actually, so it's much simpler. So this is a construction that was suggested in 2003 in a textbook by Schneier and Ferguson, and it basically says, okay, let's take a message M, we'll hash it once, and then we'll hash it again, second iterate of a function. And again, this was a suggestion to prevent length extension attacks, which it does seem to do. But the thing that's confusing is that, okay, if you would expect, of course, that if H is a random oracle, it's ideal, that if you iterated H twice, you might lose like a constant factor of 2 in the security or something, because there's 2 opportunities for collisions. But you certainly would expect nothing worse than that, right? But when it comes to indifferentiability, actually you can show that you can only have indifferentiability with very poor bounds. And so in particular, like if you tried to conclude using indifferentiability that this is collision resistant, you would at best be able to show that it's collision resistant to like 2 to the n over 4, where n is the output size, which is much less than 2 to the n over 2. Anyway, this again, it's a little bit technical. I have some slides like to describe what is the underlying intuition, but I'm running out of time, so I'm just going to skip all that. If you want to stick around, we can talk about it after the hour's up. See, there's a lot of them. Uh-oh. Here's some more implications. That's the best part. You skip all the technical stuff and get to the implications. So H squared doesn't behave like a random oracle. Can't hold with good bounds. We do a lot of work to figure out if this is something that's practically damaging, because this is all proof stuff that I've been talking about. And the closest we came was looking at a fairly natural setting called mutual proofs of work, where you're basically, two parties are trying to prove that they've been computing some hash chains, and you can abuse the properties that arise from H squared and also ambiguous key pairs in HMAC in this mutual proofs of work setting. But I'll refer you to the paper for details. We don't know. I mean, hash chains are used all over the place. I don't know if it actually gives rise to any vulnerabilities in any places. It's a good question. And so the most important practical question is like, what does all this imply about HMAC, which is used all over the place? And weak pairs could cause problems, but they really don't seem to. They're kind of like very loosely like the weak keys in DES, right? They exist, but they don't really come up seemingly in practice so much. So for example, like with colliding key pairs, you need two keys that, if you had a password and then another password, which was that password concatenated with a 0, right? If you went 1, 2, 3, 4, 5, 0, then these would be treated as the same password by the PBKDF, which would speed up, brute force attacks by a factor 2. But that doesn't quite work because actually, of course, in ASCII, like when you encode in ASCII, 0 doesn't get encoded to the bit binary value 0. So anyway, so a lot of applications seem to serendipitously avoid them. Certainly, like HKDF and some of these other things are using fixed length keys that are like uniformly chosen if they're public, and it's not a big deal. And here we can show stronger positive results about the security of HMAC in the sense of indifferentiability, which then should allow showing security of these other applications with good normal bounds like that you would expect in this setting, close to the birthday bound. Oof. So sorry. So the takeaway is that this is something to be concerned about and aware of, but doesn't seem to be threatening any actual deployed thing that we're aware of, and certainly makes doing formal analysis a huge pain. Okay, so with that, I'll just briefly reiterate. We looked at 3 different projects here. TLS 1.2 record protocol. We had a new attack that hadn't been observed before when you have short MACs. Did some new proofs. Password-based crypto, which kind of gave rise to this new definitional framework that was needed to explain the benefits of salting, and which, from a theoretical, it's pretty interesting from a theoretical perspective. We didn't quite have the right tools to even explain the benefits of some long-standing, mechanism that's used in practice, and did some proofs finally for PKCS number 5, and then we looked at HMAC and realized that in these newer settings that HMAC is not that new, but in these other non-originally envisioned settings that HMAC is being used in, there's issues with weak key pairs potentially. And we can overcome these in some cases to recover nice positive results. So from this lens of practice-driven theory, I think the message is while it's great to and certainly a useful perspective to think of theory as educating practice, I think we can also I hope I convinced you that you can also turn around a bit and use theory as a post facto tool, right? Not only to uncover, basically as a vulnerability tool, finding tool, right? When we go to try and prove things in this complexity theoretic way, we really have to nail down all the corner cases. As we saw, the corner cases come up, and apparently these weren't realized before. So it's a great way to suss these subtle issues out. Of course, it helps at least give some rigor to some intuition and informal security goals. And in the best case, of course, we can prove something which isn't the final word on security. Of course, that only is, if it's secure when deployed in a system, but can certainly improve our confidence when we can show proofs. And then, maybe also surprisingly that, contrary maybe to some people's opinions, cryptographic practice is excellent inspiration, I think, for new theory, right? Things that we hadn't really considered before. So if you go look at standards, you're not just doing a community service to try and understand security of deployed products, but which is what maybe theoreticians say. But you can actually also pop out really interesting new theory that can be quite compelling. So with that, I'll take more questions, and thanks. Just waiting for someone to ask me to go back through all those slides. Yeah. No, I'm just kidding. Sorry, go ahead.
Is there an easy way to see why single instance encryption security does not imply multi-instance to a hybrid argument?
Well, so the hybrid argument would, right, yeah, so good. So this is a great question. The question, why doesn't single instance security prove multi-instance security? Because you'd expect a hybrid argument would do it. And that's true. You could show a hybrid argument that would take the Q over Cn bound that we had before and give you a new bound in this setting, right? But that new bound would have a factor of m in front of it, right? And that factor of m would be on the top, the numerator, not on the bottom. And so actually what we would be showing is mq over Cn, right? Which is exactly opposite what we want to show, which is q over mcn. Right, so it's too loose is the short answer to use a hybrid argument. Yeah. And more generally speaking, in this multi-instance security setting, we're really worried about very small advantages, right? Because it's no longer just like the security of one instance, but it's security of many instances. And so if you, I don't know, think about, well, don't think about what I was just about to think about. It doesn't make any sense. But we're dealing with very small advantages, and we have to be very careful to make sure we preserve them in our reductions. And this is where some of the other technical complexities come up too in doing the proofs, right? So
why do you think the multi-instance security definitions never caught on in the academic community? It seems like it was presented in 2000 and then people moved on.
Well, the multi-user instance.
Multi-user, yeah.
Okay. Well, so that's a good question. I mean, I think recall the multi-user and multi-instance are, despite the poor naming conventions perhaps that we chose in this recent paper, are different, right? So one's looking at, I mean, I think the way to conceptualize is multi-user is like the weakest link security. As soon as the weakest of all of the instances or users is broken, then all the security goes away. And multi-instance security, we're asking that instead that, the attacker has to break not just the weakest link, but he has to break all the links, right? And so you get this ability to measure things like Q over MCM here. So I don't know. I mean, I think there is the reason the multi-user security notion, which is the weakest link notion, didn't catch on is that in most settings it doesn't really matter whether you analyze it in the hybrid, if you analyze in the single instance setting and then just use a general hybrid argument, or use multi-user. My recollection, and I'd have to go back and read the original paper from 2000 again, is that they were doing that particularly to analyze constructions that were like using the same randomness across multiple users, or doing other things that were kind of non-standard and for efficiency purposes, and you needed that framework. But for like normal situations where you have independent instances, you do fine using the normal single instance security notion. But yeah, we'll talk more later if you want. Yeah.
Okay, so I'm just wondering this notion of multi-instance. I feel like it's a little bit similar to like harness amplification of like encryption schemes, where like you first do a secret sharing and you encrypt many instances. Yep. Yeah.
I mean. Okay, so I'm cutting you off. Go ahead.
Yeah, and another maybe so in your definition, I feel like it's like harness amplification is somewhere like inside this, because you are like from Q over C, and you like make it stronger to M times C, and yeah.
So I mean, I guess if I might, the question is like, what's the relationship between this and the traditional hardness amplification literature? The answer is very involved, actually. So for example, like this XOR, this XOR measure smacks very directly of like XOR lemma type constructions. Yeah. But like in an XOR lemma type construction, the construction is actually the construction is actually that you XOR the bits from these hardcore predicates, and the adversary's goal is to guess that bit, right? Whereas here we're doing something slightly different. We have independent challenge bits that are separate from the construction, and the goal is to guess the XOR of all those bits. Yep. Okay.
Can you view that? First, I sample a bit B, and then I share that to B1 and B2, and
oh, and share it. I guess you could. Those would be independent. Those would be distributed the same, but.
So that's what I was.
Yeah, but the construction is not. Yeah. So, but, I mean, you're absolutely right. There's a lot of connections, and we've only like scratched the surface on exploring the connections, and indeed, like so yeah, there's a lot of work. So you can use the same types of techniques that have been used for like Unger has this paper about analyzing, whether you can show AND security is implied by XOR security in their context in kind of a general setting. Which does apply here actually, but it's a partial result, and you have to do some mapping between the two. So yeah, we're not trying to claim that like this isn't related to hardness amplification. In fact, it is, and lots of the same techniques will probably arise, and maybe there's connections we haven't even seen yet.
Yeah, another slightly related question is like, so can you go back to that advantage?
Other way.
Probability of
This way? This is what's wrong with having too many animations. Yeah.
Yeah, because in this setting, the dictionary size is small. Traditionally, we were thinking about like something negligible, but in here, like there couldn't be anything negligible.
Yeah, so I mean, yeah, clearly if n is like really, really big, like 2 to the 1,000, then it hardly matters whether you're attacking 1 million or 10 instances. Yeah, here, we're really worried about concrete security here. So like asymptotically, it's not clear that you get any benefit from these. It's, again, it's somewhat subtle to think about this stuff asymptotically. So it's really, we're trying to preserve concrete security, right? So. You can think that like if you're trying to break M L Gamal instances or M DDH instances or sub, we would expect again that the best you can do is like M times the time of the best known attack would be the kind of obvious approach to break like lots of instances. And there you have individual negligible instances, sure, but we could also hope to gain that extra log M security parameter like improvement by like having to break many in parallel. That probably made no sense. We should talk about it offline. Yeah.